Any questions about anything from last time? Or about anything? So let's see, homework 1 is due in Gradescope tonight. You can reach Gradescope through Brightspace, our Brightspace page. And homework 2 is on the home page, and it's due next Wednesday. This will be the basic pattern. I'll release the homework early in the week, like Monday or Tuesday, and it'll be due the following Wednesday. That will be the pattern. And I'm thinking about exam 1 being an in-class exam the week before spring break. So if any problems, I'll send out a more definite date, but it'll give us time to adjust it if we need to. Yeah.
And there are 2 exams in this class.
And the second exam will be a take-home exam.
Okay.
Much less stressful, I hope. Questions about anything? Let's see, there's some remarks I should have made at the end of the last hour. Last hour was kind of really, Friday was great stuff. It was about cardinality and orders of infinity. And I should have made some remarks that when S is a set with n elements, like 1, 2, 3, etc., out to n, then you say the cardinality of S is n. It's the measure of the size of the set. And it was George Cantor who started thinking about cardinal numbers for infinite sets. And he came up with, let's see, before I do that, the power set, remember, that's equal to the set of all subsets. Why is that happening? Sorry. The set of all subsets of S. And the cardinality of P of S, let's see, cardinality of this piece of S is 2 to the n. When it's a set of size n, then the cardinality of the set of all subsets is 2 to the n. And that's why it's called the power set. That explains why they called that thing the power set. Terminology. And so, it's weird. George Cantor invented some symbols. Cardinality of n, the natural numbers, is aleph naught. So that's backslash, curly stuff, sub naught. Looks like that. It's a letter in the Hebrew alphabet and also in various Arabic languages. So that's called aleph naught. It's an ancient letter. It's just fun to write. And so the power set, remember Cantor proved his theorem, is that the cardinality of the power set is basically strictly bigger. You can't find an onto map from natural numbers to the power set. So it feels like a bigger set. And so he wrote the cardinality of the power set is 2 to the aleph naught. Got to practice making alephs. Okay, and then he also realized that the cardinality of the real numbers is bigger than the natural numbers. So the cardinality of all real numbers is C for the continuum. That's what the C stands for. And so the continuum hypothesis is that those two things have the same cardinality. That's a very famous thing, and it's a mind-blowingly difficult concept, and it depends on a lot of philosophical facts, like whether or not you believe the axiom of choice. So the famous continuum hypothesis that Ralph Cohen cracked in my lifetime, but not yours, is that, basically is that C is equal to 2 to the Aleph naught. That cardinality is the same. And that there's no cardinality between N and that cardinality between Aleph naught and 2 to the Aleph naught. So C. That's really fascinating stuff. I took 3 semesters of mathematical logic at Michigan, which I really enjoyed. I'm going to say some more things about how mind-blowing some of that subject can be. And I took another semester in grad school at MIT on set theory. And so I've heard lectures galore about this material, and it's really fascinating. Questions about anything? Well, you're supposed to read 2.1 for today, and it's kind of might seem rather dry. The idea is to axiomatize the real numbers so that we understand it like we understand geometry, theorem, proof, etc. And I can demonstrate to anybody and convince them that something is true if I use the basic facts about the real numbers. That's the plan. We won't get too carried away with it. A famous person, very interesting person, he was a high school teacher in Germany, Richard Dedekind. And he was working on understanding the foundations of mathematics at a very deep level and leaving nothing to chance or feeling. Yeah, leaving nothing to feelings. You've got to understand why things are true and how to demonstrate them. So I actually read this book. It was a Dover book you could get for cheap. It was about 100 pages long. And it was in German, so I was trying to learn German and math at the same time. Was sind und was sollen die Zahlen? I guess in German you make nouns in capitals. Actually, I read it cover to cover, and it was kind of excruciating. The great thing about reading German math is you only need to about 10 words. But the math was harder to read. So first, Richard Dedekind focuses attention on the natural numbers, 1, 2, 3, 4, 5, 6, 7, 8. And everybody feels about the natural numbers that, you understand them by making notches on sticks, basically. And, you can add 2 things by sticking the sticks together, and multiplying things by taking a row of sticks and stick them together. So everybody has this gut feeling about what the natural numbers are. And Richard Dedekind wrote this crazy book where he said, okay, 1 we're going to associate with the empty set. And 2, we're going to associate with the set consisting of the empty set. And 3 we're going to associate with the set consisting of the empty set, etc. So it's very much like notches on a stick. Instead of notches, it's basically curly brackets in pairs. Anyway, he boiled down the natural numbers to making this definition, and then he proved all the basic facts that everybody believes about the natural numbers. And of course, the big fact is very much like the Peano postulates. Peano was messing around with the same kind of stuff. Similar. We'll see. What's different between Peano and Dedekind is that Peano was describing the axioms, but Dedekind made a model for the natural numbers. So it's similar to Peano's work. And of course, math induction is the biggie when you start adding, talking about what the basic facts are about the natural numbers. Everybody knows about addition and multiplication and zeros and inverses, etc., and factoring, but math induction lets you get deep results, and that's an important part of it. But Dedekind came up with this model. There's a thing in math called model theory. Peano sort of thought, okay, n exists. We're not going to say what it is. Okay, that was exciting. What I want to mention a little bit today is this is the beginning of mathematical logic. Cantor and Dedekind sort of started the whole subject, mathematical logic. And I'm going to mention a mind-blowing fact that was in my 3rd semester at Michigan of math logic. We finally could prove Gödel's incompleteness theorem. It's a mind-blowing fact. Question.
Wasn't that theorem, or I'm not sure if I'm remembering this correctly, but wasn't that like the entire coming up with that theorem like a response to that whole system with the sets?
Yeah. So Gödel took Dedekind's work and perfected it. So he had to think about not just this model of natural numbers, but all possible models of the natural numbers, and whether or not that theory was consistent, etc. Meaning you couldn't. If I told you the rules, maybe it's possible to deduce a contradiction, which means the whole subject is garbage. And so Gödel was wrestling with those kind of concepts at a much more advanced level. And he was an incredible genius. I don't know when somebody would have figured this out without him. He did it in the 1930s. Anyway, I'm going to tell you what Gödel's incompleteness theorem is in a little while. And what the chapter 2 here is about is we want to get the basic axioms for R, the real numbers, and so we can think about real numbers the way we think about natural numbers. So the the field axioms, you've seen them before in math classes. The field axioms hold for any field, including the field of real numbers. You can see them on page 24. And that's in section 2.1. I'm not going to write them here today because you've seen them before and they look incredibly natural. And I should explain that when you're doing this business, there's some dumb-sounding theorems. I'll call them baby dumb-sounding theorems. On that same page. It's just because you want to have a minimum number of axioms. Those baby dumb-sounding theorems everybody believes them and says, oh yeah, those are obviously true. You don't want to add them as axioms because they follow from the simpler things. So that's why we deal with a couple days of proving dumb-sounding theorems that everybody believes from the axioms. It's a good thing to sit through and read, so read them carefully, because I'm not going to do them in class because you'd think I'm crazy. Read them carefully and believe them, and you'll have a couple exercises to do similar things. The reason we're doing those is we want a minimum set of axioms. So if I can demonstrate something from some previous axioms, it'd be tempting to add it as an axiom, but I don't have to. So we want a small set of axioms. Otherwise, we'd add those trivial things as axioms. But we don't have to because they follow. So somebody had to make some decisions about what the axioms were going to be, and this sort of took time. I guess I'll tell you what the Gödel incompleteness theorem is. There are always facts about real numbers, about natural numbers. There are always facts about real natural numbers that are true but not provable by the rules. I'll put it in quotes because I didn't tell you what the rules are. The rules are the rules of deduction plus the axioms, which would include the principle of mathematical induction. Okay? So, Fermat's last theorem was not understood before Andrew Wiles came up with his proof, which, by the way, takes some major liberties with the rules. They had to construct a whole bunch of wild and crazy things in algebraic geometry to talk about the proof of Fermat's last theorem. So it kind of bends the rules in some sense. But it wasn't known if maybe that's an unprovable thing. Maybe it's true and unprovable, and that means math is kind of hopeless. That I want to prove Fermat's last theorem, and it's true, but I can't. That's the scary thing. But Gödel proved, he actually came up with he put his hands on this thing, which is mind-blowing. It's kind of like a diagonal argument from Cantor. It takes about 3 semesters before you can feel comfortable talking about how to do it. But not only that, but you could take that unprovable thing and make it an axiom. So let's say P equals the unprovable or unprovable statement. Then you can add P or not P to the axioms and still have a consistent system. Okay? And then you add that stupid state, let's say you add P. Then another one of those unprovable things pops up. There's an unlimited number of unprovable things. So it kind of deflated the confidence that mathematicians had that if it's true, I'm going to be able to prove it someday. It totally blew that out of the water. Anyway, it's a fascinating thing. And if you get into logic, it's an exciting subject to study. I just wanted to say the words today because you hear them. People talk about it all the time. without really explaining what the heck it is. Questions? Okay, so now I'm going to get back down to earth. You've seen from the natural numbers, you toss in a zero, that's an exciting moment in history when somebody thought of the zeros. And then another exciting moment is they added in the negative numbers. And then the Greeks in their geometry started thinking about rational numbers. And Dedekind, of course, defined the rational numbers from the natural numbers in a very careful, precise way, and has the axioms for rational numbers all figured out. And then you want to go from the rational numbers to R. And of course, everybody has the feeling of what R is. It's the real line. So that's the feeling. That's the R feeling. But of course, Dedekind wasn't satisfied with the R feeling. He wanted to define the real numbers in a very precise way, just the way he did with the natural numbers. And it was very disturbing to the Greeks. They were thinking the rational numbers were all the numbers. And it was very disturbing to them that they discovered irrational numbers. They called them incommensurate. And so, for example, the Greeks used geometry to convince themselves that square root of 2 is irrational. Really bugged them. Ir in the sense of not. And I'll prove this today because it's a fun thing to. I've probably seen it before, but it's fun. So let's see the proof of that. Let's suppose 2 is the square of a rational number p over q. And when you express a rational number, you learned in junior high that you can factor out common factors. So I'm going to assume that p and q, there's a word for that, are relatively prime. Meaning they have no common factors. Okay, so this is kind of depends on knowing that you can factor integers. So I'm going to write p as p1 to the n1. These are prime numbers, p1. I'm going to go 2, 3, 5, 7, etc. So they're in the proper order. Out to p sub capital N to the n sub capital N. So that those would go 2, 3, 5, 7, etc., 11, dot, dot, dot. Those would be the p's. Okay, and q would be a q1 to the m1, q2 to the m2, dot, 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 q sub m, capital M, to the m sub capital M. Okay, so when I divide those two things, let's say one of those terms, one of those p's was equal to one of the q's. I guess I'll think about this for a minute. P over q would be equal to blah, blah, blah. Let's suppose I had a pk to the nk. And on the bottom, I would have a q, which was the same. So I'll put the qk, q sub L is going to be equal to P sub k. So this is how you would show that you would cancel out common factors. So let's see, this is Q sub L, so this would be to the M sub L. Then you realize you could cancel them. If the ML was biggest, then you could cancel out the ones on top, and you could leave the PK in the Q. So what if ML is the big one? Then this term would be equal to 1 over PK to the ML minus NK. And that would be one of the factors in Q and not in P. And if ML was less, then the term would be PK over 1, and here we'd have the NK minus M sub L. And so that PK belongs in the P, but not the Q. So that's the way I could get rid of any common factors. That's how you would do it in junior high. So this is a remark about how you show rational numbers have a unique representation as P over Q, where P and Q are relatively prime. Okay, so now let's think about what it would mean if 2 was P squared over Q squared. 2 equals P squared over 2Q squared, which would mean that 2Q squared equals P squared. Okay, let's write that now. That would be 2 times Q1 to the M1 times Q2 to the 2M2 dot 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 QM to the 2MM, and that would be equal to P1 to the 2N1 times P2, etc. and to the 2NN. And here's the aha moment. P1 would have to be 2. Not 2 factorial. Oh, it is 2 factorial, but it's 2. And not only that, so P1 must equal 2. It's the first prime, and 2 divides that thing on the right, so P1 has to be 2. But it's P1 is there to an even power. N1 is bigger than or equal to 1. So we see that 2 squared divides the right-hand side. RHS for right-hand side. And there's only 1, 2 hanging out in front of the thing on the left. That means 2 has to divide one of the Q's. I mean, in other words, Q1 has to be 2. So a 2 must divide the product of Q's, of powers of Q's. It's because it's unique factorization that makes this work. So Q1 must also be 2. But remember, P and Q have no common factors. That's a contradiction. P and Q have no common factors. Contradiction. My lightning bolt symbol for contradiction. And so that means my assumption must be wrong. There's no such rational number. So that's how you do it. Questions about that? Yeah. Let's see. 2 divides the thing on the left. So it divides the thing on the right. So because of unique factorization, that means 2 appears in the unique factorization. And the P1 is the first prime. So I mean the smallest prime in the factorization. That makes sense to you? It's unique, yeah. The fact that this follows from unique factorization. The book proves this in a somewhat more formal way, but it's exactly the same concept. And they don't say the word unique factorization as much. That's exciting. So it freaked out the Greeks, and Dedekind wanted to figure out, okay, how do I deal with the real numbers so I understand what the square root of 2 is? And so he came up with this brilliant idea. Actually, this is much better than his thing for n with the curly brackets. He came up with something called Dedekind cuts, which in German are called Schnitz. Okay, so we identify, his big idea was to identify a real number. R with, he cuts the rational numbers into 2 pieces, namely the Q, the rational numbers in Q such that Q is less than or equal to R. So if R is a rational number, then R would be in that thing. But the square root of 2, so see that would cut the rational numbers into these ones that are less than or equal to R, and then the ones that are bigger than R. So there'd be 2 sides of rational numbers. Okay, and the square root of 2 would correspond to, let's see, that would be the set of Q. Let's make it in Q plus, such that Q squared is less than 2. Of course, there's no Q that's equal to 2. We know that now. And then we'll toss in the negative ones, let's say the Q, such that Q is less than or equal to 0. Okay, so what does that do? That cuts the rational numbers into, I'll do dot, dot, dot. The feeling is the rational numbers are dense in the real numbers. And we'll make sense of what that word means. So they're all over the place. They never get up to the square root of 2. And there's none above the square root of 2. So it cuts the rational numbers into 2 sides. The sides whose squares are less than the square root of 2, and the side whose squares are bigger than the square root of 2. And he defined that to be the square root of 2, that cut. And it was a breakthrough, because then he could prove that this definition of the real numbers had all the properties we needed to understand analysis. We needed to understand the least upper bound principle and completeness of the real numbers. This allowed him to deduce those facts from definitions. So it was a model for the real numbers. Exciting moment in history. I'm not going to get carried away with that kind of thing because it's a sort of a historical thing. This book takes sort of the facts about real numbers and tells you what they are. rather than going way down to absolute foundations of bedrock. But I wanted you to hear that word of Dedekind cut because it's a beautiful thing. Okay, so that brings us now, the algebra properties of the real numbers are very kind of ho-hum and well known from junior high. The order properties are a little bit deeper and maybe require some more discussion. The order properties of R. And of course, the urge is to make them axiomatic, like we did with the algebra properties. And to make sense of an order and the real numbers, we define R plus to be the R and R that are bigger than 0. The book uses P for that. Blackboard bold P, that's that font. Okay. But sometimes I forget what the P is supposed to be, and I prefer R plus because it's more meaningful. Okay, so what does it mean for a real number to be bigger than another one? Okay, and here's what it is. Here's number one property. If A and B are in the R plus, then there's the sum. Is A plus B. If A and B are in R plus, then so is the product. And 3, if A is a real number, I'm not using R plus there, then exactly one of these things has to happen. Exactly one of the three things are A is either in R plus, A is 0, or minus A is in R plus. Okay. So people who thought deeply about what order means came up with these three things which sort of distinguish R and make it so well ordered. This thing is called the trichotomy property. Three things are possible, but only one of them has to happen. And yeah, I couldn't do this for the complex numbers. I couldn't come up with an ordering like this. Real numbers are special in that way. Okay. And now I can tell you what it means for something to be bigger than another one. So let's suppose I have A, B real numbers. A less than B, which is the same as B greater than A, means that B minus A is in R plus. And A less than or equal to B, which is the same as B greater than or equal to A, B minus A, oh, maybe it's an R plus, but it could be 0. So union 0. Okay, so this is another moment where I want you to read the book because they prove some very basic facts you know from junior high about inequalities using the axioms. So once again, carefully read the theorems on page 27 and their proofs. Particular one of them is interesting. A theorem. Here's one of the typical theorems on that page. If A is in R and 0 is less than or equal to A is less than epsilon for any load epsilon. Then A must be 0. In other words, there's no smallest positive real number. If I can squeeze it over, if I can push it to the left, it means I can push it all the way to 0. That sounds kind of dumb, but it's the kind of thing we need to be comfortable with. So basically this means there's no smallest positive real. I want to do something fun before this hour is over. I want to use the basic facts about inequalities to demonstrate the famous fact. The fun thing. If A and B are positive real numbers, then A times B to the 1/2 is less than or equal to A plus B over 1/2, over 2. Okay, this thing is called the geometric mean. And this side is called the arithmetic. The geometric mean is less than or equal to the arithmetic mean. Okay, let's think about that. Let's first think about the case A equal B. That's kind of a dumb case. When A is equal to B, that would be A squared to the 1/2 on the left, which is A. And on the right, it would be A plus A over 2, which is A. So duh, it holds when A is equal to B. Well, what about the case the next case would be A unequal to B. Well, if A is unequal to B, then the square root of A would be unequal to the square root of B. Why would that be? Yeah.
I would guess, like, just thinking back to what we were talking about earlier, they would probably have different, like, prime factorization.
Oh, these are real numbers. They're not rational numbers. I'm not trying to trap you or anything, but if square root of A were equal to square root of B, then when I squared them, I'd see that A is equal to B. But A is not equal to B. That's how you would do it if somebody said, prove it to me. And so I guess since we're being ridiculously picky today. Otherwise, square see that A is equal to B, and that's a contradiction because A is not equal to B. Okay? All right, so those two things are unequal, and that means I can take square root of A minus square root of B, square it. All right, square root of A minus square root of B is a non-zero thing, and so when I square it, I get something that's strictly positive. That follows from the axioms of order, basic facts that you believe and know without saying them. Okay, so what does that mean? When I square that side, I would get square root of A squared is A minus 2 times the square root of A times the square root of B plus B is greater than 0. Okay, and voila, there it is. So let's see, I would have A plus B is greater than 2. Square root of A times square root of B is the square root of A times B. And so there it is. In fact, I get a strictly greater than 1. That's kind of interesting. So the only time equality can happen in that inequality is if A equals B. So that fact part 2 only get equality in square root of AB is less than A plus B over 2 when A is equal to B. Otherwise, it's a strict inequality. That's cool. Let's see, I'll finish off today by mentioning there's an n-dimensional version of the fancier version. It's fun to think about. And if you look in the book, you'll find reference to how to prove this using logarithms, natural logarithms. So if I take the product of A1, A2, dot, out to AN, and take the nth root, that's less than or equal to A1 plus A2 plus blah, 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 AN over N. So that's the geometric mean of n things on the left, and that's the arithmetic mean on the right. And there's various ways of proving it. My favorite way uses the fact that the natural log function is a convex function. Natural log of x. Let's see, I need x to be positive, is a convex function. When x is greater than 0. Convex downward. And that's the key to understanding why that is true. Any last minute questions about anything? So a big part of Gödel's theorem is that he assumed that the theory of natural numbers, which is called first order number theory, is consistent. If you assume that, then he proved that if it's consistent, there's things that are true that you can't prove. And there's a second Gödel incompleteness theorem,